Oh, hi everybody. It's Rich Halstead-Nussloch here, and I got some key points for the Six Sigma Green Belt that I want to go through with you. So this works well with your blue notebook that you got on the workshop weekend. So let's first take a look at slide 6, which shows clearly that Six Sigma is a customer-focused problem-solving methodology supported by a handful of powerful analytical tools. So the primary focus of Six Sigma has always been on the customer, what the customer wants, etc. So slide 7 shows that the reason that we want to do this is to improve our efforts to better serve the customer needs. And the bottom line is we want to ensure repeat business. So let's skip to slide 9, which shows a very important mantra. So this is something that you're going to memorize, and it should kind of center your thoughts on Six Sigma. So the mantra says for Six Sigma to be effective, we're going to do 3 things. We're going to do these things in order. First, we're going to put processes in place. Then, we're going to bring those processes into control statistically. And then finally, we're going to improve them, and we can always improve them by reducing variation. So we're going to do those 3 things in that order. So that's something that you need to learn is do 3 things and do them in order. The next couple of slides take us through the DMAIC. That's define, measure, analyze, improve, implement, and then control stages of process improvement. And DMAIC has been one of the main points of value that Six Sigma has contributed to our process improvements. One thing to note is that control, when used in the sense of the final stage of DMAIC, means that we're going to standardize and validate our process within our improved process within our system. Then slide 11 has a graphical representation of the whole DMAIC process, and it's worth some study. Slides 12 through 18 take us through Dr. Deming's 4 areas of profound knowledge. And these 4 areas are areas to understand. We study, we aim for knowledge of systems so we can understand processes. We aim for knowledge of statistics so we can understand variation. We aim for knowledge of psychology so we can understand motivation. And we aim for knowledge of knowledge so we can always improve our process improvement approaches. So these slides, 12 through 18, are worth some study and some understanding. Then if we turn to slides 19 to 21, we get a demonstration of everything varies. Now, it's important to understand this, and it's really important to understand on slide 21 that there are 2 types of variation that are oh so important. A common cause variation, which is the variation that, if you remember when you signed your name 6 times, is always present in all of our processes. And if there's too much common cause variation, we need to reduce that by acting on the system. We need to reduce that by reducing variation, by improving how our process delivers our products or services or experiences. This is distinguished from the special cause of variation, which is something like if I had gone around when you were signing your names and bumped your elbow. That would have been a special cause. So to eliminate the special causes, you need to find them and address them. So finding the special cause is key to that success of special cause variation reduction. Then if we get to slide 24, we see some of the word soup that we have to deal with in Six Sigma. In DMAIC, control means standardize and validate, as we've seen when we took a look at slide 10. On slide 24, control means that our process is predictable. So we can predict how it's going to vary in the future if it's in control. So that's some word soup that you need to manage. All right, and then slide 25 has the basic theorem of variation with a corollary. So the basic theorem of variation states, as you remember, if we always do what we've always done, we'll always get what we always got. And then the corollary to the basic theorem of variation, which doubles as Einstein's definition of insanity, is doing the same thing over and over, but expecting a different result. So learning these, this theorem and this corollary, it's something that you need to do because it will help you in the future as you pursue things in Six Sigma. All right, so slide 26 introduces us to the concept of a run chart. So a run chart is that chart where we're going to monitor our process performance. We're going to put on the x-axis of the run chart time moving forward, and on the y-axis the performance measure. Slides 28 and 31 show us about process monitoring, and we have learned on slides 28 and 31 that histograms show us process central location, process spread, and importantly process shape. So that's one thing to understand, that histograms can show us the central location through the x-bar bar of our process, the process spread through the average range, and then later on using the Shewhart formula for the process standard deviation, the process sigma, and then most importantly from the histogram, the process shape. Slide 33 and 34 talk about the central location. So we have three measures of central location of a process. We're going to use the arithmetic mean on 34 when the distribution is symmetrical or symmetric. But when it's not symmetric, it's asymmetric or skewed, is another way of saying it. When it's not symmetrical, we should use the median or the mode. Slides 40 through 42, it's a good thing for your career to memorize these facts, these math facts about the normal distribution, that between plus and minus 1 sigma, we have about 68% of the values. Between plus and minus 2 sigma, on slide 41, we have about 95.5% of the values. And then between plus and minus 3 sigma, we have 99.73% of the values. And this for about 100 years, since Shewhart instituted the statistical process control techniques, this has been conventionally assumed to represent the expected limits of common cause variation. Then on slide 43, we see what a Six Sigma level process that's centered at the midpoint of the specs would look like. Both customer specs are 6 sigma units away from the average, and so that's total span of 12 sigma. All right, slides 50 to 52 show us the important role that the histogram plays in our process analysis technique that we're going to use as a 6 sigma green belt, because we're going to use the histogram to determine the process distribution shape. And it's important to take a look at it because we're expecting a bell-shaped curve. We're expecting that our process variation is going to fall into a normal or bell-shaped curve. This is also known as the Z distribution, or the Gaussian normal distribution, or the unit normal distribution. So we're going to call it the bell-shaped curve. We're going to call it the Z distribution in this course. Slide, and an important part is we're going to construct a histogram, take a look at the shape, make sure it's a bell shape before moving forward in our process analysis. Then slides 54 to 57 talk about the role of using control charts. Now, control charts are specialized run charts. And as you remember, a run chart has on its x-axis time moving forward, on its y-axis a measure of performance. We're going to add control limits, which are on the upper part of slide 56, to a run chart and turn it into a control chart. So these control limits for the x bars, for example, are set at an estimated plus and minus 3 sigma from the process average. And these control limits are set by the process. So that's depicted on slide 57, that these control limits are set by the process. Slide 58 shows that we have another set of specification limits, and these are set by the customer. So this is what the customer wants. So the control limits are a depiction of what the process is giving us. So that's the voice of the process. Control limits are the voice of the process on slide 57. Slide 58, specifications are set by the customer. So specifications, customer requirements is another way of talking about customer specifications. Those are set by the customer, so they represent the voice of the customer. Then let's skip forward through all of the slides that you need to come up with control charts to slide 80, which is our first slide covering the Western electric rules. So the Western electric rules, as you remember, are those rules that show patterns that in control charts are non-random, and they indicate a special cause. That is, that our process is out of control. So let's kind of tick through these Western electric rules beginning on slide 81. We could have a single point outside of the control limits that indicates a special cause, and that our this pattern indicates our process is out of control. On 82, we have an adjustment pattern. This pattern is there's an adjustment throughout this control chart where the process is creeping upwards and then in one step adjusts downwards to near the lower control limit. Slide 83 shows a reduction in variability. So the first half, the variability represented here is very wide. In the second half, it's much narrower. On 84, we have 2 or 3 consecutive points near one control limit, and this indicates a non-random pattern or a special cause in our process. In 85, we have a run, and there are 2 flavors of a run, either 7 or more consecutive points, and they have to be consecutive, and they're all either increasing or they could be decreasing. What's represented here in the first half is a run of increasing points. And then we could also have 7 or more points, and they all have to be consecutive on one side of the center line, or the process average in this particular case. So in the right half of this pattern, this Western Electric rule pattern, we have 7 points below the center line. On 86, we have a cycle, and this is another special cause or a non-random pattern. And on 87, we have our final Western Electric rule, which is a trend. So this is a trend where the measurement keeps going up, basically. All of these represent that we have a process that's out of control. All right, slide 88 shows a review of our statistical process control technique, which puts control limits on a run chart, and control limits identify the expected limits of normal, random, or chance variation, and those by convention, as established by Shewhart, are set at a plus and minus 3 sigma, estimated 3 sigma units from the process average. And this leads to the control limits having 99.73% of the observations should fall between those control limits. In slide 89, we move to bringing in what the customer wants in with respect to moving to from control, having a process in control, to having a process that is capable of meeting our customer requirements. So our main measure, quantitative measure of capability is sigma level. So a process is just capable. The threshold of capability on the sigma level scale is a sigma level of 3. So this again represents that the customer specs are set at plus and minus 3 sigma from the process average. So 99.73% of the observation should fall between the customer specs if it's operating at a 3 sigma level. So slides 91 through 94 kind of tell us what we need to do, what we need to have in place before we can go ahead and calculate meaningful measures of process capability. So process capability on 91 can be measured only if all special causes have been removed from our process and it's operating in a state of control. So this leads us to slide 94, which shows that before we can meaningfully measure process capability, we have to first come up with a histogram, and that histogram has to show a bell-shaped curve of our variation, and then we have to do the control charts, and we have to demonstrate through the control charts that our process is operating in control. So we need to do those 2 things before we do any capability analyses. And then going back to slide 92, we need design specs from our customer. These are our customer specifications in order to establish and compute our capability. We need to know where the center of the natural variation is, and we get this through the X bar. And then we need to know the range or the spread of the variation. And we're going to get this through the average range and then utilize a Shewhart formula, which estimates the process standard deviation by dividing the average range of the process that we measured in the process by a Shewhart constant, little d2. All right, so then if we go ahead and we go to slide 97, we see the Z formulas show that since sigma is in the denominator, they show that as sigma, that is the process variation measure that we're going to use, goes down, sigma level, which is our process capability, increases. So a sigma level is a measure of process capability that is directly proportional with process capability. That is, as sigma level goes up, our process capability also goes up. All right, so let's skip ahead over the Z table to slide and over our example of process capability calculation problems to our final process capability problem in the slides on slide 106, which has the mention of the Motorola shift. So that an important thing to realize here that Motorola, to apply a field factor, redid the calculations after assuming that the mean had shifted 1.5 sigma. So to apply the Motorola shift, you should probably remember that you're going to add 1.5 sigma. All right, slide 108 shows two important capability indices, CP, which measures potential capability, and CPK measures true capability. So remember that CP measures potential capability, while CPK measures true capability. Then on slide 109, we see the practical importance of CP and CPK. So slide 109 says if CP is greater than 1, so CP and CPK are on a directly proportional scale, directly proportional to capability. So as CP and CPK goes up, our potential and true capability go up. All right, their threshold of capability is 1. So slide 109 says that if CP is greater than 1, while CPK is less than 1, we can make the process capable by moving the process average to the midpoint of the customer specs. Now, if CP, which measures potential capability, is less than 1, we can't make it capable. We can't make that process capable by just merely moving the midpoint of the specs. We need to reduce variation. All right, so that's slide 109. Slide 116 is an important slide to kind of get an intuitive, internalized understanding of. We have our two measures of capability that are inversely proportional to capability. These are proportion nonconforming and DPMO. That is, as they go down, our capability goes up. And then we have two measures of capability that are directly proportional to capability. That is, as sigma level and CPK go up, so does capability. All right, so it's probably a good idea to get some familiarity with the zones of not capable, the threshold of capability, and the zones of capable or more than capable for these four measures. All right, so let's skip ahead over the example problem to slide 128, which says that not only is Six Sigma a customer-focused problem-solving process improvement methodology, but Six Sigma also aims to reduce costs for the company. So there's something in it for the customer, that is reducing variation, reducing defects. There's something in it for the company to do a Six Sigma project. And what's in it for the company is to reduce costs. All right. So slides, and let's skip ahead again to slides 152, which show that there are various roles for the Six Sigma structure within the company. And it'd be a good idea to take a look at slides 152 to 160 and be familiar with the various roles on a Six Sigma project and a Six Sigma organization. Slide 163 introduces, we've been talking about, up to this point, we've been talking about the Six Sigma improvement approach of DMAIC. Excuse me. Six Sigma also has a innovation approach that's called Design for Six Sigma, or DFSS, and it uses the DMADV problem-solving approach. So slide 163, 164, 165, and 166 kind of highlight how DFSS and DMADV work together to innovate, come up with an innovative process that is Six Sigma capable, Six Sigma level capable. All right, shifting gears again on 167 to 177, we learn that lean aims to reduce waste, or Japanese for waste is muda. And so it's important to realize that customers, when they buy something, that is, they pull on a new instance or a new product or a new service through the process, when they buy something, that's the highest expression of value. And so that's what we want to do, is we want to come up with a value stream that where we've reduced the waste to the minimum. And this has come to us through, lean has come to us through the Toyota production system on 168. 169, lean is the relentless pursuit of the perfect process through waste elimination. Lean has been described by Michael George on the next slide as a process philosophy with three purposes: eliminate wasted time, effort, and material, provide customers with make-to-order products, and reduce cost while improving quality. In the U.S., Henry Ford, in the 1920s, worked essentially on waste. So you should take a look at these slides and get an understanding of how lean aims to reduce waste, or Japanese for waste is muda. So slide 182, which shows our first of root cause analysis techniques, shows a specialized, there's a flow chart there that's really specialized, and it's specialized in that it's organized to show the flow between suppliers that deliver input, which goes into our process, which translates and converts those inputs into outputs, which go to our customer, and our customer has a feedback loop. So the customer becomes, through that feedback loop, one of our suppliers. So that's known as the SIPOC model. Then on slides 182, we have beginning our root cause analysis methods. So we can use flow charts. Slide 185 shows that if we ask W questions, why, where, when, where, who, how, and then why again, that, why is probably the most important question of those W questions. Then we have various flow charts, we have check sheets, we have Paretos. It's good to understand that the Pareto is the 80-20 rule, that is 80% of the problems are due to 20% of the causes. The Ishikawa cause and effect fishbone diagrams, beginning on 194. They're good to understand as structured brainstorming. It's really good technique to get a team on the same page with respect to what they see as the problems are. And then 198, we have scatter diagrams, which of course lead us to correlation. And as you remember from your stats courses, we need to be looking at correlations, but careful with correlations, as indicated on slide 199. Then on slide 200, we have our final root cause analysis of failure mode and effects analysis, or FMEA. And this is the single most important root cause analysis in use today. It successfully allowed the United States to get to the moon and back with people. Men went up to the moon and back in the late 60s and early 70s. And FMEA played a major role. So FMEA, as indicated on slide 200, prioritizes potential failure modes in designs through what's called the risk priority number, or RPN. So if we take a look at slide 203, which is kind of the process workflow for doing an FMEA, we're going to brainstorm our potential failures, and then for each potential failure, we're going to determine its probability, its severity. Well, first we're going to determine its severity. That's number one. Then its probability, and then its controllability or detectability. So we're going to end up with three numbers. Generally, they're on 10-point scales, with 1 being at not a big problem and 10 being, major problem. On all three scales, we're going to multiply those in the step on 203, slide 203, where we assign our RPN. So we're going to end up with a number between 1 and 1,000, with the larger numbers indicating the higher priority of action. We want to get those potential failure modes out of the design. All right. So that's what I got for the slides. Again, I want to remind you that in order to be a fully capable Six Sigma professional, you need to know some Japanese. So here are some Japanese terms. Poka-yoke means mistake proofing. Kanban is a signal or a card. It's very useful in lean. It's very useful in just in time. Very useful in agile development. Kanban. Kaizen means continuous improvement. Muda, as we've learned, means waste, and the Gemba is the workplace. So if you know these Japanese terms, you'll be better off as a Six Sigma professional. Because Six Sigma got a lot of big boost, and as did Lean, in Japan in the 50s, 60s, 70s, 80s, and into the future. Also, one thing to memorize as a Six Sigma professional is the relationship with Sigma, which measures our process variability, and Sigma level, which measures our process capability. So our goal with variability and our Sigma measure is to reduce it. Our goal with Sigma level, which is our measure of capability that is directly proportional to capability, is to increase it. And luckily, as our Sigma, that is our measure of variability, goes down, our Sigma level increases. So I hope you found this review, this quick walkthrough of the notebook and some of my comments. I hope you found this useful, and good luck in your future career and your application of Six Sigma. Bye for now.